Hello.
Hello guys, hello Dave.
Hello, Jane.
So are you ready?
I'm ready.
Oops, by the way, we'll first introduce ourselves. Let's go.
Anyways, I'm Lopez&Casajeros. Taking up the course BSN Math 1B2.
Oh, it's my turn by the way. I'm Julian Lopez, taking up the course of Bachelor's Element. Oh, I'm wrong. Bachelor's Secondary Education, major in Mathematics 1B2. So, are you ready? Are you ready?
Aye, Captain.
So, we will prove to you the theorem 1, 2, 3, 4, 5, and 6. So, watch out, guys. Just sit back, relax, and enjoy.
Theorem 1 states that two intersecting planes meet in a straight line. To prove that two intersecting planes meet in a straight line, we consider that this is plane A and this is plane B. If these two planes intersect, they meet in at least 2 points, that is M and M, as it is stated in action 3. If two distinct planes cannot meet in 1 point only, it cannot be M only, it cannot be N only, it should be M and M. But M and M determine a line which lies wholly in A and also in B, not only in A but also in B. As it is stated in action 1, if 2 points of a straight line lies in a plane, then the whole line lies in a plane, hence, the plane have the straight line M and M in common.
Theorem 2. A plane can be determined by a point in a line not on it, by two intersecting lines and two parallel lines. A plane can be determined by a line and a point not on it. So let's consider this illustration. Point D and point E lies on the line L. Then, one and only one plane, which is plane A, can be passed through line L and point J, because one and only one plane can be passed through D, E, and J. And this is supported by the action 2, which says that through 3 non-collinear points, one and only one plane can be passed. A plane can be determined by two intersecting lines. Let's see this illustration. Point D is the intersection of line 1 and line 2. Point F lies on line 1 and point E lies on line 2. DEF determine that plane B in which line 1 and line 2 lies. This is supported by action 2, which states that through 3 non-collinear points, one and only one plane can be passed, and action 1, which states that if 2 points of a straight line lie in a plane, then the whole line lies in the plane. A plane can be determined by 2 parallel lines. So let's look at this illustration. Line 1 and line 2 lies on plane C. Point F lies on line 1, and points D and E lie on line 2. These 2 lines, which lie on the plane C, determines a plane, which means that these 2 lines are parallel.
Theorem 3, if a line is perpendicular to each of 2 lines at their point of intersection, it is perpendicular to the plane of these lines. Given a line L perpendicular to each of line 1 and line 2 at the point of P. To prove that L is perpendicular to line 1 and line 2, let M be the plane line 1 and line 2, and let line 3 be a line, any line in plane M through P. Draw a line meeting L1 and L2 and L3 in the points B, C, D, B, C, and D, respectively. Corollary 77. If each of two lines is perpendicular to the third line at the same point, then the plane of two lines is perpendicular to the third line.
Theorem 4. Through a point, there is one and only one plane perpendicular to the line. To prove the theorem 4, let us have or see this illustration. We have given the line L and the point P. To prove that through this point P, there is one and only one plane perpendicular to the line L. So, through this point P, we will draw two lines, the PR and the PR prime. Then, this plane A, determined by the two lines PR and PR prime, is perpendicular to the line L. To prove this, it is supported by the Corollary 77, which states that if each of these two lines, which is perpendicular to the third line, which is the line L, at the same point, which is point P, then the plane, which we consider this plane A, of these two lines is perpendicular to the third line.
Theorem 5. Through a point, there is one and only one line perpendicular to plane. Given a plane M and a point P. To prove that through P, there is one and only one line perpendicular to plane M. When P is in the plane M, let line 1 be any line in M through P, and let N be a plane perpendicular to line 1, and P and meeting M in line 2. PA be a line in N and perpendicular to line 2. Then PA is also perpendicular to line 1. Theorem 71. Line and a plane perpendicular to each other. A line is said to be perpendicular to a plane if it is perpendicular to every line in the plane passing through its foot. In this case, the plane is also said to be perpendicular to the line.
Theorem 6. Oblique lines from a point to a plane, meeting from a plane at equal distances from a foot of the perpendicular are equal, and conversely, two equal oblique lines from a point to a plane meet the plane of equal distances from the foot of the perpendicular. To prove the theorem 6, let us see this illustration. Line PC is perpendicular to the plane M. AC is equal to BC, in which both of them are in the plane M. To prove, since PC is perpendicular to CB and BC is perpendicular to CA, both of them are congruent and have 90 degrees. And PC is equal to PC because of reflexive property of equality. Triangle PCB and PCA are equal because of the SAS postulate, or side angle side postulate, and we therefore conclude that PA is equal to PB because of the CPCTC, or congruent parts of congruent triangles are congruent. Triangle PCB and PCA are equal because of the SAS postulate or side angle side postulate, and we therefore conclude that PA is equal to PB because of the CPCTC or congruent parts of congruent triangles are congruent. So, have you learned something? Have you learned something?
Yeah, that's right. I learned how to prove theorems 1 to 6.
Wow,
Let's encourage them.
so that's great part. So, guys,
Encourage.
we hope that you learned something from what we have discussed a while ago. So, for more info, just log on www.facebook.com/solidgeometry MS 2022. So, guys,